Hey everybody, just want to do a quick video to cover today's lesson. First thing I want to mention before we get into the actual notes portion, I guess, is factoring quadratics. This is the very back page of the packet that you received. An algebraic concept we make sure really clean and really good at, particularly for this unit and the next, is factoring. So just gave you some basic factoring problems here that you might want to run through and go and check it out. Make sure you're good with like difference of squares and factoring a GCF, of course our trinomials. You got some grouping type stuff going on. So just make sure you have those skills sharpened up, and we can check those when I get back. But the primary part of our lesson today is investigating area under a curve. So this initial part is something you've already done before. We did on the LTF with like the semicircle and the trapezoid and the triangle, where I kind of had made you find some areas of those shapes. So let me do this first one with you just so you can get an idea of what I'm looking for. So you have f of x is equal to x plus 1. What we're going to do is just graph this. So we know that x plus 1 would typically have a y-intercept of 1. So we put a point right there at 0, 1. Then we have our slope, which is 1. So we go up 1 to the right 1. And we'll go ahead and probably put them all on the graph this time. And we go down, or you can go down 1, left 1. Okay, so here's our line that we would have created from that. Pull that down a little more. There we go. All right, so what this means right here in these little braces, circle it, this part is saying take only the x values from 1 to 3. Okay, so 1 to 3, that'd be from here to here. Okay, so we're only looking at that portion. We're going to find the area between the curve, our blue line right here, and the x-axis. So we're looking for, let me just shade it real quick, the area of that shape. And so when it asks all of these, you can see I have 2, 3 on this problem, 1, 4, and so on and so forth. It's asking you to determine what's the area between the curve that you graph and the x-axis between those x intervals. So within that interval of x's, rather. So part A, you can see we're going from 1 to 3. We have a trapezoid. All right, so this height right here, it looks like it's 2. We could plug 1 in just to double check it. We can definitely say that f of 1, I'll just write over here, f of 1 is 1 plus 1, which is 2. So we're talking about this point, the best spot, which is important. So it's our height, which happens to be the length of that base. Like you can eyeball that, but if you weren't able to see it, then you would just plug it in to determine the answer. All right, so the next one is f of 3. So if I said f of 3, it looks like it's 4, and we can verify that. 3 plus 1 is definitely 4. So that's this point right here. And so the distance from 0 to 4 is the length of 4. And we already know the distance between 1 and 3 is 2. And so we're just going to find that area, which is our trapezoid. So the area formula is we're going to take our bases and add them together. So we have this 2 right here that I'm shading in black, plus this base 4 times our height, where our height is right here, the distance between the bases, so times 2, all over 2. So our area is 6, we'll just say square units. All right, so 6 square units, or units squared, same thing. So now what you do is just do the exact same thing on the remainder of the problems on this page. You have different shapes, you have some piecewise, and then obviously you can compare with a key. I do believe that this one, in fact, let me pull it up before I mismake this statement. I do have that changed on the key. Yes, -2, 5. So instead of 0 to 8 on letter G, go ahead and change that for me, please, to -2, 5 is the x interval that I want you to be working with. So do those and then check your answers, please. Okay, so now that we've done those problems that you're very familiar with, it's just, trapezoids, triangles, rectangles, shapes that you're accustomed to find the area of. What I want to do now is, if you can see, this is a little bit different. These are not straight-edged shapes, polygons, that you're typically used to working with. These are curves. These are not straight. So we can't find the exact area, at least not yet, of these shapes. So what we can do is we can approximate them. All right, and so you can see there's a bunch of different bullet points up here with what's called left-hand and right-hand rectangles. We call them Riemann sums, and I can discuss that a little more when I get back. But what we're going to do, since we can't find the exact, we're going to approximate it, and we're going to use a shape that we're very comfortable with to determine the area of, and that's a rectangle. So there's our shape, or here's our graph, rather. Okay, we're going to do the left-hand rectangles. So this table over here represents points on our graph. So I'm going to take the first two x values we have right here. We have 0 and 30. So 0, I'm going to put a little point right there at 0, and I'm going to put a point right here at 30, right on the x-axis. Since it says left-hand rectangles, I'm going to go between these 2 points, between 0 and 30. The one that's on the left would be the 0. So I'm going to put my pencil on 0, and I'm going to go all the way up until I hit the graph. And that happens right now. So there we go, hit the graph. And then we're going to bring that rectangle straight across and then back down, and there's our first rectangle. We call it a left-hand rectangle because the height of this rectangle, which is this distance right here, that height is the left side of the rectangle. Okay, so let me continue this process. The next 2 points, I'll do it in red, are 30 and 40. So put a point on 30, put a point on 40. The point that's on the left is the 30, so put the pencil on 30, go straight up until I hit the curve, flatten across to create a rectangle, back down, and there's our second rectangle. We're going to continue that process all the way through until we've captured all the rectangles that we can for our graph. So the next one, let's just go 40 and 50. So 40, 50, 40 is on the left, so we go up, just flatten our rectangle out, come back down. Okay, let's go 50 and 70. So 50, 70, 50 is on the left, so we go straight up until we hit the graph, flatten across to create a rectangle, back down. Okay, our last, we have colors here. So it'll be 70 and 90. 70 and 90. 70 is on the left, so we come up, across, and back down. And so now we've covered the portion that we're interested in as far as finding the area. So what we're going to do is we're going to determine the area, or approximate the other area rather, using those rectangles. So our area is approximately. So our first rectangle here we know is 10 to 30, which is a base of 30. And our height, well, we know it's all the way up to 20. We can see that, and it's on the graph over here. So our first rectangle would be 30 times 20. We're going to continue that process. So our second rectangle, we're going to do that in red, is 10 times the height of our rectangle, which is the distance from here to here. So that'd be 30. You can look at our table once again to verify that. You can see that that particular point right there gives us a value of 30. That's our height. All right, now go orange. 10. So the first one we have is 20. Then we have 30. Now right here at 40. That's our height. Height of 40. Distance between 50 and 70 is 20. So 20 times our height, which is 55. Make sure we use that table since those values are given to us. Don't just approximate by what the graph looks like. Then our last rectangle, right here. I guess I'll get the color right one time. Here you go. Last one. I'll put this one. There we go. All right, so this distance between 70 and 90 is 20. So plus 20 times our height, 65. There we go. So what we need to do from here is just take all those numbers and do the math, do the arithmetic to determine what our approximate area is for this graph. So I'll let you do that for a moment. It looks like we're going to get approximately 3,700. Once again, we're doing units squared. Now, one question that there's a lot of conversations we need to have from here. The one thing I want to mention is that we obviously don't have an exact area. It's approximated like we've been talking about. And you can see right in here, all these gaps that I'm shading in black right now. Okay, it didn't capture those parts. So if I were to ask, hey, is that an underestimate or overestimate? We would definitely say this is an underestimate. So that'd be a common question I'll ask you, hey, is that approximation an overestimate or an underestimate in this particular case? All right, so that's left-hand rectangles. Okay, so just to make sure we're clear, everything's there. So the next thing we want to do is we're going to do the exact same thing. We're going to approximate. We're going to use right-hand rectangles instead. Okay, so it's very similar thought process. I'm going to erase this. We'll write down that 3,700 that we figured out from earlier. It's right here. 3,700 units squared, that's what we determined. So now we're going to do the same thing, but use right-hand rectangles. So our first two x values are 0 and 30. So put a point on 0, put a point on 30. This time, we're going to pick the point on the right, since it's right-hand rectangles. So out of 0 and 30, 30 is on the right. Then go up, hit the graph. Once you hit the graph, flatten the rectangle back out and come back down. So there's our rectangle. This time we're going to the left to create our, go up, back to the left to go capture that other point. Okay, so the next rectangle we would do is 30 to 40. 40 is on the right, so it's on the right side. Go up until we hit the graph, come out, flatten it out, come down, there's our second rectangle. So let's just continue that process. We would have 40 to 50. 50 is on the right, come up, to hit the graph, come back down, there's our rectangle. Now 50 to 70. It's on the right, the 70 is on the right, so we come up, hit our graph, flatten our rectangle out, come back down. Then our final 70 to 90. Pick the point on the right, go up, hit the graph, flatten across. There's our last rectangle for our right-hand rectangles. And then we're going to continue the exact same thing we did earlier. Determine the area. So I'm going to use this space. So our approximate area, well, like we said earlier, this is 0 to 30, so that's a distance of 30. So 30 times the height. Well, this is not the same height as the last one. You can see that the distance from our base up to this spot is 30. We can verify that. We go back here and look. Remember our first, I'm going to highlight it right here. Our first rectangle is this one, 0 to 30, which has heights of 20 and 30. You can see that it's not the 20 this time that's the height, but rather the 30 that's our first height. So it's 30 times 30. We'll continue that process. Next one. I should have done that in blue, sorry y'all. 30, 30, our blue rectangle. All right, so now our red one. And those 10. And we're going to have a distance all the way up to this time, 40. You can verify that. You can see the height is 40 right there. Okay, now our orange rectangle, distance of 10 for the base. And then our height that goes up here, touch the graph at that spot. Well, we can come over here and see that that's a height of 55. Using our table. Now it's the black rectangle. Distance of 20. The height is on our graph. that spot, which would be the point at the height of 65. And then last, 20, our height, which is 70. So once again, we'll go through here and do our calculations to determine what our area is. I'll let you do that. I'm getting 4,550 square units for our approximation. And then this time, you can see that we have actually space that's over the curve. So we're having additional area that's not underneath that curve. So this would be an overestimate. Of what the actual area is. Okay, so then the last thing over here says average. It says trapezoid. So what we're going to do is we're going to take the 3,700. So just another way for another approximation. The 3,700 that we got from the left-hand rectangle sum, and our 4,550. If I can squeeze it in there. Sorry. And we're going to determine that average of those two quantities. So we're getting 4,125. Square units. Okay, so what I want you to do now, you can look at the key that's on, work these and then check the key rather, that's on Canvas. But as you're doing these, I want you to think about a couple things. Like when is underestimate occurring? When is an overestimate occurring? See if you can determine or anticipate when that's going to occur. Sometimes you might not be able to tell. It might be the same, actually. But there are some instances where you can tell right off the bat, hey, it's going to be an underestimate, it's going to be an overestimate, and recognizing that's going to help you. Other things is I want you to draw these rectangles in on 2B, and then you can see 2C has one where it's increasing and then decreasing. So draw those rectangles, get familiar with them, and then we're going to talk about some strategies, probably next class, that maybe will help you get through those quicker. This is a common question on the AP test in calculus. Actually, what we're doing, like I said, it's Riemann sum. This is what it's called, and they like to ask this question. If you can figure out really quick ways to do it, which we will cover in class, then it'll make that problem very quick for you to finish. So the next thing I want to talk about, so you do 2B and 2C, like I said. Check those answers, please. When you finish those, all right, let's look at midpoint rectangles. Once you get those done, you can come to this part of the video if you want to pause it, and then when you're finished, come to this spot. So I'm going to do midpoint rectangles very quickly. So they decided they liked left hand, right hand, so someone came around and said, well, how about we do midpoint as well? So all right, let's do midpoint rectangles. So I'm just going to do two rectangles. So the first rectangle, I'll just come over here. I'm going to do in this portion, we have 5 points. So I'm going to take 0 to 50. So I'm going to take our entire interval 0 to 100, so it makes sense. If we're just doing two rectangles, we don't have to do it this way, but if we did two rectangles, I'm going to make it where it's cut in half this time. So 0 to 50. Well, the point that's in the middle, is this 25, 90. All right, y'all can see that, 25, 90. So we're going to actually have that spot be our height of a rectangle. Because remember, earlier it was the left side, so that was our first point. Then it was our right side, which is our second point that we're using. But this time, we're not going to do a left-hand rectangle. That would be from 0 up. We don't want that. We don't want a right-hand rectangle. That would be from 50 up. We're going to go right in the middle. Well, the middle between 0 and 50 is 25. And you can see that we have a point that matches with that. So I'm going to come from 25, I'm going to go straight up, make a point, okay, which our table is telling us is a y value of 90. So from there, we're going to draw a rectangle. So I'm going to come straight up on this left side, go through the graph at that point that we made, that's in the middle, and then come back across and come back down to create our first rectangle there in blue. Okay, we're going to do the exact same process. Let me erase this, kind of help us see a little bit better. So now we're going to do 50 to 100. So 50 and 100. 75 is obviously in the middle. And we have that point given to us, 75, 60. So right here in the middle, you know that's a y value of 60, although it's not very good. Don't let the scale over here on the left throw you off. But we're going to draw a rectangle. So there's our two rectangles. All right, and so we know, erase this again, that our first rectangle has a base length of 50. And a height, remember we use this point right here, so a height of 90. So 50 times 90. Okay, then our second rectangle there in red, remember has a base length again of 50. And then a height, where we use this point, 75, 60, to determine the height. So 60 would be the height of our rectangle. And we're going to do those values to determine our approximate area. So let you do that real quick. Not too bad of a problem. So we're looking at approximately 7,500 square units. Okay, that's typically what we have. Left hand, right hand, which is more common. Then every once in a while they like to throw in the midpoint rectangles. Okay, so the last thing that I want to talk to you about is that there is another approach. It's called the trapezoidal method. And so if we have trapezoids instead of rectangles. So let's look at one of these and see what it looks like. So it says approximate the area. Here's our function. Y equals x squared plus 5, and it tells us our interval from 0 to 5 by calculating the sum of trapezoids with widths of 1. So widths of 1, pretty simple. We're going to go over here to our table. First interval, x value in our interval is 0, so it's 0. And then since it says widths of 1, that means our next x value will be 1. We continue our process. 2, 3, 4, and 5. So now we have our x values for our problem. And then to determine our f of x values, or y values, we just take those and plug them in. So we're going to plug 0, plug it into our equation for x, which would be 0 squared plus 5. So 5. Then we'll plug in 1. 1 squared is 1, plus 5 is 6. 2 squared is 4, plus 5 is 9. 3 squared is 9, plus 5 is 14. 4 squared is 16, plus 5, which is 21. 5 squared is 25, plus 5, which would be 30. So now we have those points. Let's go ahead and plot them on our graph. 0, 5. 1, 6. Not much of a difference there. 2, 9. 3, 14. 4, 21. A little lower. 4, 21. And then 5, 30. So you can see this quadratic that we're interested in. Now, the only thing we're concerned about is from 0 to 5, so I'm going to go and block that off. Here, 0, all the way up to 5. I'm going to try that one more time. So there we go. All right, so there's our region. We're determining the area. Like I said, it has to have widths of 1, so I'm going to go through here, and we're going to draw all those points that we had. I'm going to draw all the way straight down, back down to those given x values. So you can see that the width right here, on every single one of these, is 1. All right. So next thing, trapezoid. You need to determine the base lengths. Okay, well, our bases, if you look at it, this one here in red, here's our first base. Okay, our first trapezoid is sitting right here. Our first base, well, the height would be 5. That was the point. We first plot the 0, 5. So this height is 5, or this base rather, is 5. And then with our second base right here, that I've just now highlighted, okay, that would be 6. And our third would be 9. I'm just working off those y values from the table. And then we're going to have 14. Squeeze it in there. Okay, here's our next base from here to here. 21. And our last one, 30. Okay, so we've labeled all those different bases. Now what we're going to do is we're going to determine the area of those trapezoids that we can create. So, the very first one. If I were to take these and connect, right? And I take this height and this height, and we connect them, you can see we have our first trapezoid right now here in black. So the area of that trapezoid, no, I just shaded right over the number. Just want you to see visually what it was. So the area would be the sum of the bases, 5 plus 6, times the height, which our height is 1, divided by 2. Okay, now we're going to do the exact same thing. Second trapezoid, I connect them, draw them down. There's our second trapezoid. It would be 6 plus 9, that's our basis, times our height, divided by 2. And continue that process. And the next one's from here to here. Our next trapezoid, so 9 plus 14. Times our height, divided by 2. All right, fourth trapezoid. From here to here. Connect those heights. Draw them down. So we have a base of this one right here being 14 all the way to 21. So 14 for the first base, 21 for the second. The height, once again, is 1 divided by 2. And our final one, from here to here. Our base is 21 times our other, or rather added to our other base, 30, times the height of 1 divided by 2. So we have our 5 trapezoids that we can work with to determine the area. And there's different ways you can kind of work with this problem as far as if you didn't have a calculator, how you want to find that area. They all have 1/2s if you want to factor out the 1/2. And it's just a really large adding problem. But if you want to get that to or determine our approximation, which I should have done that over here, approximate area, change that. So let me give you just a little bit of a moment to determine that area, and you can check together. Okay, so I'm getting something like 135 over 2 square units. And if you want to get that decimal, that's fine as well on this problem, just to have a little more of a intuitive thought on it. 67.5 square units. So I guess you might wonder, like, why would we even use trapezoids when we already have rectangles? Well, you could see, if I was talking about this, how close is this compared to the actual area? You can see that in this particular case, our trapezoids actually fit the graph better than our rectangles were in some of the problems we were doing earlier. So this might be a more accurate representation of our actual area for this problem. So there's some other things we can talk about as far as how do we make these approximations more accurate. But I think that's better done in person, and I can go over that with you guys when I return. There should be an assignment for you to look at and work on. It's like a little LTF activity. Work on that for the remainder of the class, please. Make sure you have that factoring handout at the back of this as well working on. Make sure those skills are taught. And then I will answer any questions when I return. You guys have a great weekend. Stay out of the trees.